Hello everyone, in this video we're going to look at one example which will help us to review and wrap up Poisson process, random variable, as well as exponential random variable. So in this example it says earthquakes occur in the United States according to a Poisson process having a rate of 0.25 per day. Suppose we begin counting earthquake at some point in time. So in this problem, what is given is the rate of arrival, right? So that's your lambda in in the formulas that we will use later. The rate of arrival or the rate of occurrences. What is the probability, part A, that 6 earthquakes occur in July 2050? So the main important point to answering these problems is to differentiate between exponential random variable and Poisson random variable. Poisson is referring to the number of arrivals. Exponential is referring to the time between arrivals or inter-arrival time. So we're going to have to distinguish those two in these problems. The first one is probability that 6 earthquakes occur in July 2050. So what you see here is that the probability is referring to the 6, or the number of arrivals or number of occurrences. And the time is given. So the July 2050 is your time, which is given. Probability, but is referring to the number of arrivals. And whenever the probability is referring to the number of arrivals, that's a Poisson. So your random variable here is n of t, and the t is how many days? 31 days in July, right? So t is 31 days, and we're talking in days because the lambda is in days. So n of 31 is our random variable here, which is Poisson with the parameter alpha. And if you remember, alpha is equal to lambda t. So lambda 0.25 times 31, that's 7.75. That's the parameter of this Poisson random variable. So you can say n of 31 is a Poisson with parameter 7.75. Now the probability that we're trying to calculate here is probability that this random variable n31 is equal to 6, number of arrivals in 31 days. So if you go back and take a look at the Poisson Pmf, it's e to negative lambda t to x over x factorial. So in this case is e to negative 7.75 to 6 over 6 factorial. And if you calculate that, you're going to get 0.129, about 13% chance that you see 6 earthquakes in 31 days. And I want to point out an important point here is that it doesn't matter that it's July or if any other 30 days period. As long as it's 30 days periods, the probability is the same. It can be half of June and half of July. It can be 5 days from so many different months. As long as the duration is 31 days, that's all that matters, the t. So that was Poisson because it was number of arrivals within a given time frame. Now part B, what is the probability that 2 or more earthquakes occur over a 50-day period? Again, it's the same situation. The probability that you're going to calculate is referring to the number of arrivals, 2 or more, and the time period is given, 50 days. So that's your t. So essentially your random variable here is n50, which is Poisson of alpha. Alpha is equal to lambda t, 0.25 times 50. And that is 12.5 5. So it's a Poisson of 12.5. That's how you define your random variable. If you're asked later to define your random variable, you're going to have to define it this way. And now the probability that we're calculating is probability that n50, number of arrivals in 50 days, is 2 or more. So that means greater than or equal to 2. So right there are a lot of possibilities. 2 arrivals in 50 days, 3, 4, 5, all the way to infinity. And that's a lot of probability to calculate, and then you have to sum them up. So in these situations, you know that the best way is to convert this to 1 minus probability of n50, complement of that, less than 2. So now all you need to do is to calculate n50 equals to 0 and 50 equals to 1, which is basically 1 minus probability of n50 equals 1 minus probability of n50 equals to 0. So you're going to have to calculate these two the same way we calculate them here. And I'm just going to write it in terms of summation. So it's a summation over x from 0 to 1 e to negative 12.5 to x over x factorial. And if you replace x with 0 and 1, sum over, you're going to get 0.99, which is very high probability, and makes sense because if the rate of arrival is 0.25 per day, meaning that every 4 days you're expecting to see 1 earthquake, there is a really good chance that in 50 days you see 2 or more. So that's why this probability is very high. Let's move on. Part C. On average, how many earthquakes will occur in 2052? It turns out that that year is a leap year. So the t that is given to us is 366 days. And what we're asked is on average. So it's expected value of number of occurrences in 366 days. So again, you're calculating an average or expected value of a Poisson random variable because it's referring to how many, not how long. How long or the time between arrivals is exponential, but here is Poisson. So we're doing expected value of n 366 days. And you know that it's equal to lambda t, expected value of Poisson. So 0.25 times 366 days will give you 91.5 earthquakes. So on average, we're going to see 91.5 earthquakes in a year, in a leap year. On average, how long will it between, so again, it's how long, so it's referring to a time, so that's why it's exponential. And obviously, I mean, you can see that it's a time between arrivals, inter-arrival time, between the 100th and the 101 earthquakes. So time between 2 consecutive arrivals obviously is exponential, and we want to know the expected value of that on average. So expected value of time between arrival. In this case, it is t of 101, but it really doesn't matter. Expected value of t is the same for any inter-arrival time. So that is 1 over lambda. That's the expected value formula for exponential. And it is You know that. 0.25 or 4 days. Right? Every 4 days you're expecting to see another earthquake on average. Part E says, what is the probability of no earthquakes over a 5-day period? Again, the probability is referring to the number of arrivals, so that's why it's Poisson. It's not about time between them. The time is actually given. That's the t. So the random variable here is n of 5, number of arrivals in 5 days. And you want to calculate the probability of that being equal to 0. No earthquake. So e to negative lambda t to x over x factorial times 5 to 0 over 0 factorial. It's going to be e to negative 1.25. So this is 1, and this is 1. So 0.286. So about 28% chance to see no earthquake in a 5-day period. Part F, what is the probability of no earthquake over 5 separate 1-day periods? So this is the point that I mentioned earlier. There is no difference between part E and F here. The T is the duration, and both of them, the duration is 5 days. It doesn't matter that it's 5 separate 1 days or if it's 10 separate half a days or 5 consecutive days. All it matters is the duration, right? Duration matters. And that's 5. So essentially we're doing the same probability, which is going to be the same. So no difference between part E and F. What is the probability of no earthquakes in the period June of 2050 to August of 2050? So you're going to have to figure out how many days is that. So June, July, and August. If you sum them up, the T is 92 days. And we're doing probability of no occurrences, no earthquakes. So probability of N92 being equal to 0. Following the same formula, we're going to have e to negative lambda t, this is t and lambda is 0.25, multiply them, it's 23 to 0 over 0 factorial, and that is very close to 0. So almost no chance of seeing no earthquakes in 92 days. Part H, what is the probability of 24 earthquakes in the period, same period? So instead of 0 earthquakes that we had here, now 24. So all we're doing is probability of N92 this time equals 24. That's just going to be e to negative 23 to 24 over 24 factorial. And that's going to be a little more, 0.079, about 8%, about 8% chance that you'll see 24 earthquakes in that time period. So that was the example that we needed to work on to review both exponential and Poisson in this module. Thank you.